We often think of space as, this beautiful but kind of static thing up there. But the reality is, well, it's constantly changing. It's kinetic, sometimes violent. Space is always remodeling itself. You have galaxies colliding, stars being born, and sometimes the very stuff of the cosmos getting ripped apart. Today, we're diving into a discovery that really captures this chaotic side, but on a scale that's almost impossible to imagine. It's a colossal cosmic structure linking galaxies, they're calling it, the cosmic gas bridge.
It really is an incredible finding. It gives us such a clearer picture of how galaxies interact. We're looking at a new paper here. It's from the International Center for Radio Astronomy Research, IQR, and published in the monthly notices of the Royal Astronomical Society.
Okay, so our mission for this deep dive. First, we need to really get our heads around the numbers. The scale of this bridge and its gas tail is just staggering. Then we need to unpack the mechanics, this sort of surprising two-part process that created it all. And maybe most importantly, we'll talk about why tracking this specific stuff, neutral hydrogen, is so fundamental to understanding star formation, the future of galaxies.
Right. And just to set the scene, we're talking about two relatively small galaxies here, about 53 million light years away. They're called NGC 4i52 and DDO 137 dwarf galaxies. It's their interaction, plus their sort of unfortunate location near a much bigger cluster, that really made this whole thing happen.
All right, let's start with the structure itself, the anatomy, if you will. Bridge sounds almost mundane, but what exactly did the astronomers find linking these two galaxies?
Well, they found this enormous stream, this massive structure made entirely of neutral hydrogen gas. This isn't stuff you see with a regular telescope. It's not emitting visible light. It's the cold, raw fuel, basically the ingredients for future stars. And the scale, like you said, that's where it gets wild.
Tell us about that scale. I hear it dwarfs even our own Milky Way.
Oh, absolutely. The bridge part itself, the bit connecting the two galaxies, that stretches 185,000 light years across space. But the really jaw-dropping part is this enormous gas tail they found at the same time. It extends outwards for, get this, 1.6 million light years.
Whoa, hang on. 1.6 million light years. That's, what, nearly 10 times the size of the Milky Way?
Pretty much, yeah. And this tail, this 1.6 million light year structure, it's actually the longest one of its kind ever detected in this sort of interacting system. It's just a phenomenal indicator of the sheer energy involved.
So how do you even see something like that? It's huge, it's diffuse, it's invisible gas, and it's 53 million light years off. What kind of tech lets you map that?
Yeah, you definitely need specialized gear. Radio astronomy is the key. This work used data from the Wide-Field ASKAP L-band Legacy All-Sky survey. Thankfully, they call it WALLABY for short. It uses CSIRO's ASKAP radio telescope in Australia, and its whole purpose is basically to map out where hydrogen gas is distributed across the universe.
So WALLABY wasn't looking for shiny stars. It was specifically hunting for this cold, dark fuel hiding between the galaxies.
Exactly right. One of the co-authors, Professor Kinji Becky, pointed out that it's these kinds of high-resolution studies of neutral hydrogen that let them see these structures. They'd be completely invisible otherwise. It really takes the sensitivity of a telescope like ASKAP to detect this faint diffuse gas being stretched out over such, well, frankly, monumental distances.
The scale is just mind-bending, but maybe even more so is figuring out how it got like that. How did forces manage to create this bridge and then rip out a tail 1.6 million light years long? What's driving this cosmic tug-of-war?
Right, so the lead author, Professor Lister Stavely-Smith, and the team confirmed it takes sort of a 1-2 punch, two different physical processes. The first one is kind of what you'd expect, gravity, specifically tidal forces.
Okay, tidal forces, like the gravitational pull between NGC 4532 and DDO 137 as they orbit each other, that pulling starts stretching the gas out between them. Makes sense.
Yes, exactly.
Yeah.
That gets the stretching started, forms that initial bridge structure, but that doesn't explain the enormous tail, especially how it's so long and mostly on one side. For that, you need something else, a powerful environmental factor.
And that's where their location comes in, right? They're not just floating in empty space. They're near the huge Virgo cluster of galaxies.
Precisely. And this is where the second mechanism, ram pressure, becomes the star of the show, particularly for that incredible tail. See, these dwarf galaxies aren't just interacting with each other. They're also physically falling towards the center of the Virgo cluster. And that cluster is filled with this incredibly hot, dense gas.
How hot are we talking? What kind of environment are they plunging into?
Well, the sources say the gas cloud surrounding the Virgo cluster core is about 200 times hotter than the surface of our sun. It's a really extreme environment. So as the galaxies speed up and plow through this superheated intergalactic medium, they face this massive headwind, essentially. That's ram pressure.
Okay, let me see if I've got this. Tidal forces pull gas out between the two galaxies, forming the bridge. But then, as the whole system falls towards Virgo, this ram pressure acts like a cosmic wind, stripping gas off the back of the system and stretching it out into that incredibly long tail.
That's a great way to put it. The ram pressure literally strips the gas away and heats it up too. This combined effect, the internal pulling from tides and the external stripping from ram pressure, dictates the whole shape and ultimately the fate of all that gas.
Professor Stavely Smith used a really good analogy for this, didn't he? He said it wasn't like a sudden explosion, but more like a slow burn over a billion years.
Yeah, that was a great comparison. He likened the whole billion-year stripping process to how a satellite burns up when it re-enters Earth's atmosphere. You know, that friction, that stripping away of material. Imagine that, but happening to entire galaxies and stretched out over a billion years.
A billion years. That time scale is just hard to process. It really shows how even the most dramatic cosmic events unfold over these immense periods, all driven by fundamental physics.
And the physics backs it up. When they looked at the numbers, the density of the electrons in that hot cluster gas, the speed that dwarf galaxies are moving, it all fits. It's enough to explain how such a huge amount of gas got pulled away and stretched out. It really demonstrates how a galaxy's local interactions can be completely overwhelmed, or at least dramatically changed, by the larger environment it lives in, especially a hostile one, like a massive cluster.
Right. Okay, so we have what's an enormous bridge and tail structure, and the how this combination of tidal forces and ram pressure. Now, let's get to the why. Why does this matter? Why should we, or you listening, care about this giant ribbon of hydrogen gas 53 million light years away? What's the so what here?
Well, it boils down to something we could call
Mm-hmm.
galactic starvation. It's a really critical insight. We know that neutral hydrogen gas is the absolute basic raw ingredient needed to form new stars. So if you can track where the hydrogen is going, you understand where stars will be born in the future, or where they won't be.
Ah, okay. So mapping this gas isn't just about seeing what's there now. It's like looking at a forecast for future star birth, or star death, I suppose.
Exactly. This finding is super important for understanding how galaxies evolve, particularly when they fall into these really dense, harsh environments, like the Virgo cluster. When galaxies get pulled into these clusters, the ram pressure doesn't just reshape them aesthetically, it actively removes their fuel supply for making new stars.
Right. And this system, NGC 4532 and DDO 137, it's like a perfect case study. That huge 1.6 million light-year tail of gas. That gas isn't going back to the dwarf galaxies, is it? It's lost.
It's effectively lost to them, yes. It's being ejected out into the vast space between galaxies, the intergalactic medium. It won't be forming stars in those parent galaxies anymore, which tells us a lot about why some galaxies and clusters seem to stop forming stars while others outside keep going. Studying this specific system helps us understand these galactic life cycles, how clusters act as environments that can shut down star formation over time.
Something else that really stood out was a connection Professor Stavely Smith made, something maybe a bit closer to home for us. This type of interaction, it's not totally unique, is it?
No, not at all. He specifically pointed out that the dynamics they're seeing between NGC 4532 and DDO 137 show strong similarities to our own galactic neighborhood, specifically the way the Milky Way interacts with the Magellanic Clouds. The large and small Magellanic Clouds are nearby satellite galaxies.
That's fascinating. So this distant system, being stripped of its gas, could actually be giving us a sneak peek at the processes happening, or maybe that will happen right here in our local group as we gravitationally interact with the Magellanic Clouds.
It certainly provides a valuable comparison. We can study the physics of gas stripping and redistribution there in that extreme Virgo environment and apply those lessons to better model what might be happening or could happen to the gas associated with the Milky Way and the Magellanic System.
Okay, so let's try to wrap this up for you. In this deep dive, we've explored this ICARA research that paints a picture of the cosmos as incredibly dynamic. We looked at this massive gas bridge, 185,000 light years long, and an absolutely record-breaking gas tail stretching 1.6 million light years. Just enormous.
And we saw how it formed through a kind of cosmic double act. Internal tidal forces started the stretching, but the intense ram pressure from falling into the superhot Virgo cluster gas did the major stripping over a billion years.
And critically, this matters because tracking that neutral hydrogen, the star fuel, shows us how these huge cluster environments can essentially starve galaxies, stopping them from forming new stars. It's a window into galactic evolution.
Which leads us nicely to a final thought to leave you with. Given that this system, NGC 4532 and DDO 137, was quite similar in its interactions to our own Milky Way and Magellanic Clouds, and knowing now how effectively gas can be stripped and lost during these interactions, what might that imply for the long-term future of star formation right here, in our own galactic backyard? If our own dance with the Magellanic Clouds is also ejecting significant amounts of star-forming fuel out into intergalactic space, well, what does that mean for the future generations of stars in the Milky Way and its companions? That's maybe the big question this kind of research leaves us pondering.